Welcome. Today we are looking at redox reactions at an advanced level. This is a key topic in your chemistry exams for SS3. Pay close attention. Let us begin. First, let me review what redox reactions are. Redox is short for reduction oxidation. Redox reactions are chemical reactions in which electrons are transferred from one substance to another. Oxidation is the loss of electrons. Reduction is the gain of electrons. These two processes always occur together. When one substance loses electrons, another substance gains them. The substance that loses electrons is oxidized. It is called the reducing agent. The substance that gains electrons is reduced. It is called the oxidizing agent. Redox reactions are everywhere. They occur in batteries, respiration, photosynthesis, corrosion, and many other processes. Understanding redox reactions is essential for understanding chemistry. Now let me explain oxidation numbers in detail. Oxidation numbers are a way of keeping track of electrons in a chemical reaction. They are also called oxidation states. An oxidation number is a positive or negative number assigned to an atom. It represents the number of electrons that an atom has gained, lost, or shared. The sum of oxidation numbers in a neutral compound is 0. The sum of oxidation numbers in a polyatomic ion is equal to the charge of the ion. Some rules for assigning oxidation numbers are important. The oxidation number of an element in its free state is 0. For example, Na, Cl2, O2, and Fe all have oxidation number 0. The oxidation number of a monatomic ion is equal to its charge. For example, Na plus has oxidation number +1. Cl has oxidation number -1. The oxidation number of hydrogen is usually +1, except when it is bonded to metals, then it is -1. The oxidation number of oxygen is usually -2, except in peroxides, where it is -1. The oxidation number of fluorine is always -1. The oxidation number of alkali metals is always +1. The oxidation number of alkaline earth metals is always +2. Oxidation numbers are useful for balancing redox equations. They help identify which species is oxidized and which is reduced. Now let me explain how to balance redox equations using the oxidation number method. The oxidation number method is used to balance redox equations. The first step is to assign oxidation numbers to all atoms. The second step is to identify the elements that change oxidation number. The third step is to determine the change in oxidation number for each element. The fourth step is to multiply the formulas by coefficients so that the total increase in oxidation number equals the total decrease. The fifth step is to balance the remaining atoms. For example, consider the reaction between copper and nitric acid. The unbalanced equation is Ku plus HNO3 equals KuNO32 plus NO2 plus H2O. The oxidation number of copper changes from 0 to +2. It increases by 2. The oxidation number of nitrogen changes from +5 to +4. It decreases by 1. To balance the changes, multiply the nitrogen species by 2. The equation becomes Cu plus 2HNO3 equals CuNO32 plus 2NO2 plus H2O. Now, balance the remaining atoms. The balanced equation is Cu plus 4HNO3 equals CuNO32 plus 2NO2 plus 2H2O. The oxidation number method is useful for balancing redox equations. Now let me explain how to balance redox equations using the half reaction method. The half reaction method is commonly used for reactions in aqueous solution. First, write the two half reactions, one for oxidation and one for reduction. Balance each half reaction for mass and charge. Multiply the half reactions by appropriate factors so that the electrons cancel. Add the half reactions together. Simplify if necessary. For example, consider the reaction between potassium permanganate and iron 2 sulfate in acidic solution. The oxidation half reaction is Fe2 plus equals Fe3 plus E. The reduction half reaction is MnO4 plus 8H plus 5E equals Mn2 plus 4H2O. Multiply the oxidation half reaction by 5. Add them together. The electrons cancel. The balanced equation is MnO4 plus 8H plus 5. Fe2 plus equals Mn2 plus 4 H2O plus 5 Fe3 plus. This method works for all redox reactions. It is especially useful for reactions in acidic or basic solutions. Now, let me explain electrochemical cells. An electrochemical cell is a device that converts chemical energy into electrical energy. It is also called a voltaic cell or galvanic cell. A voltaic cell consists of two half cells. Each half cell contains an electrode and an electrolyte. The two half cells are connected by a salt bridge. The electrodes are connected by a wire. In the anode half cell, oxidation occurs. Electrons are released. In the cathode half cell, reduction occurs. Electrons are consumed. The electrons flow from the anode to the cathode through the external circuit. This produces an electric current. The salt bridge allows ions to flow. It completes the circuit. The voltage of the cell is the difference in electrode potentials. The electrode potential is a measure of the tendency of an electrode to gain or lose electrons. Now let me explain standard electrode potentials. Standard electrode potentials are measured under standard conditions. Standard conditions are 298 Kelvin and 1 atmosphere pressure. The concentration of ions is 1 mole per cubic decimeter. The standard hydrogen electrode is used as the reference. It has a potential of 0. The standard electrode potential of a half cell is the voltage of a cell composed of the half cell and the standard hydrogen electrode. The standard electrode potentials are listed in tables. The electrochemical series is a list of elements arranged in order of their standard electrode potentials. Elements at the top of the series are good reducing agents. They lose electrons easily. Elements at the bottom of the series are good oxidizing agents. They gain electrons easily. The standard electrode potentials can be used to calculate the cell voltage. The cell voltage is the difference between the cathode potential and the anode potential. The cell voltage is a gray cell, is gelijk aan a gray cathode, a gray anode. A positive cell voltage indicates a spontaneous reaction. A negative cell voltage indicates a non-spontaneous reaction. Now, let me explain the Nernst equation. The Nernst equation relates the cell potential to the standard electrode potential and the concentrations of ions. The equation is E equals E degrees, RT, divided by NF ln Q. E is the cell potential. E degrees is the standard cell potential. R is the gas constant. T is the temperature. N is the number of electrons transferred. F is Faraday's constant. Q is the reaction quotient. The Nernst equation is used to calculate the cell potential under non-standard conditions. It is also used to calculate the concentration of ions. The Nernst equation is important for understanding electrochemical cells. Now, let me explain the applications of electrochemistry. Electrochemistry has many applications. Batteries are electrochemical cells. They convert chemical energy into electrical energy. Primary batteries are non-rechargeable. They cannot be recharged. Examples include dry cells and alkaline batteries. Secondary batteries are rechargeable. They can be recharged. Examples include lead-acid batteries and lithium-ion batteries. Fuel cells are electrochemical cells. They convert chemical energy into electrical energy. They use hydrogen and oxygen. They produce water as a byproduct. Fuel cells are used in spacecraft and cars. Corrosion is an electrochemical process. Iron corrodes to form rust. Corrosion can be prevented by painting, galvanizing, and alloying. Electroplating is an electrochemical process. It is used to coat one metal with another. Electroplating is used to protect metals from corrosion and to improve appearance. Electrochemistry is essential for modern technology. Now let me explain the electrolysis of water in detail. Water can be electrolyzed by adding a small amount of acid or base to make it conductive. At the cathode, hydrogen gas is produced. H plus ions gain electrons. The reaction is 2H plus 2E equals H2. At the anode, oxygen gas is produced. OH, ions lose electrons. The reaction is 4OH, 4E equals 2H2O plus O2. The overall reaction is 2H2O equals 2H2 plus O2. Electrolysis of water produces hydrogen and oxygen gases. Hydrogen is used as a fuel. Oxygen is used in many industrial processes. Electrolysis of water is a promising method for producing clean hydrogen fuel. A common exam question asks you to balance a redox equation using the half reaction method. Here is a sample answer. First, write the two half reactions, one for oxidation and one for reduction. Balance each half reaction for mass and charge. Multiply the half reactions by appropriate factors so that the electrons cancel. Add the half reactions together. Simplify if necessary. For example, MnO4 plus 8H plus 5 Fe2 plus equals Mn2 plus 4 H2O plus 5 Fe3 plus. Another exam question asks you to calculate the cell voltage using standard electrode potentials. Here is your answer. The cell voltage is the difference between the cathode potential and the anode potential. The cell voltage is Y cell, is gelijk aan Y cathode, Y anode. A positive cell voltage indicates a spontaneous reaction. A negative cell voltage indicates a non-spontaneous reaction. For example, if the cathode potential is plus 0.34 V and the anode potential is negative 0.76 V, the cell voltage is plus 0,34, 0,6 plus 8,8 V. Another exam question asks you to explain the Nernst equation. Here is your answer. The Nernst equation relates the cell potential to the standard electrode potential and the concentrations of ions. The equation is E equals E degrees, RT divided by NF ln Q. E is the cell potential. E degrees is the standard cell potential. R is the gas constant. T is the temperature. N is the number of electrons transferred. F is Faraday's constant. Q is the reaction quotient. The Nernst equation is used to calculate the cell potential under non-standard conditions. Let me give you a quick summary. Redox reactions involve the transfer of electrons. Oxidation numbers keep track of electrons. Oxidation number method and half reaction method balance redox equations. Electrochemical cells convert chemical energy into electrical energy. Standard electrode potentials measure the tendency of an electrode to gain or lose electrons. The Nernst equation relates cell potential to concentrations. Electrochemistry has many applications, including batteries, fuel cells, corrosion, and electroplating. Practice these concepts. When you have them down, move to topic 7.